Algebra 2 students, today we are going to be discussing an important concept of functions and their inverses. So you've already seen inverse functions when we talked about inverse sine, inverse cosine, inverse tangent. But now let's just study inverses in a more general sense. The inverse of a function f of x is called f inverse of x. It reverses the action of that function. So we're borrowing a notation, f negative 1 x. This is not a negative 1 power. This is read as f inverse of x. F inverse of x. And it is the inverse function. It reverses, right? It undoes what the function f does. We know two functions are inverses of one another if f composed of g of x equals x and g composed of f of x equals x for all values in the domain of the respective interior functions. And that becomes a pretty critical idea later. So inverses in general, here's what they are. So let's talk about some of the properties of inverses. The graph of an inverse is a reflection over the line y equals x, and this will be really important when it comes to how you find an inverse. So take a look at the red function and the green inverse of the function. Notice they intersect on the line y equals x, and they're mirror reflections over that line. Look at the red f of x here and the green f inverse. Look at the red f of x here and the green f inverse. There are functions that never touch the line y equals x, and then the inverse of that function never touches the line. It's reflected over this line, and it looks something like this. By reflecting over the line y equals x, inverses have a property where the domain and range actually flip. So if you have a function f of x with a domain and a range, the inverse of that function, the range of this function is its domain, and the domain of this function is its range. So that's important, and you can see that as evidenced here by the graph. Now, another important idea is this horizontal line test. So remember the vertical line test. We knew something was a function if it passed the vertical line test. So this is a function, and this is not a function. But if we have what's called the horizontal line test, what it talks about is its inverse would not be a function. So if I flip this over the line y equals x, and I get the following shape here. Do you see that the reverse of that function would fail the vertical line test? Sorry, the inverse of that function would fail the vertical line test. So the horizontal line test is the idea that you can see if a horizontal line crosses a graph of a function more than once, then there's no inverse. That is technically true, it's not technically true, it is true, but there's a way that functions, if they're going to fail the horizontal line test, we make them pass it. So a great example is the sine function. The sine function looks like this, and it goes on forever in each direction. Pretty clear that that fails the horizontal line test. Well, the way we make it pass the horizontal line test is we only define it from here to here. And if I only define it from here to here, guess what? When I take the inverse, it passes the horizontal line test. So to make functions have an inverse, we will sometimes restrict the domain and range so that it passes the horizontal line test. As a result, we end up getting inverse functions that don't work for everything. So I will tell you, when you use inverse sine, the only values you can get over here, when you take the inverse sine of some value here, let's call it x, the only possible values over here for y have to be between 90 degrees and negative 90 degrees. even though there's a lot of angles that have a sine of a certain value, the inverse sign can only spit out values in a certain range because of this restriction. Anyway, I digress. How do you find the inverse algebraically? So you can take a function like f of x equals 3x minus 2, and you can see how we make this function up. The first thing we do is we take an x, we multiply it by 3, and then we subtract 2. So the inverse is doing the opposite operations in the opposite order. You would take an x, and the first thing you do is add 2, and then divide by 3. And you would get this. Now the following example worked out is a much nicer way of finding that inverse. So the way we would find this inverse, the first thing is replace f of x with y, and then switch x and y. This is that idea that y equals x. If y equals x, let's switch them. Now solve this new equation for y. I add 2, then I divide everything by 3, and now once you get y by itself, you replace that y with f inverse, because that's what you have found. You'd found the inverse there. So the way you find a function algebraically, replace f of x with y, solve for y. When you isolate y, you've found the inverse. So let's try another example. We'll come back to that idea in a second. So let's try another example, something like f of x equals x squared minus 3. So to find the inverse, start with y equals x squared minus 3. Now switch x and y and solve for y. I'm going to add 3 to both sides. I'm going to take the square root of both sides, and I get the square root of x plus 3 equals y. Now, I will tell you the graph of this function right here looks like this. And the graph of this function down here looks like this. So what we ended up doing when we found this inverse is we only found the inverse of this positive part. And the reason for that is actually when you take the square root, you have to account for the negatives, and so the negative part would actually be this other part here. But notice this isn't a function while this is. It passes the vertical line test. So when we find the inverse, we have to worry about those things. Just incidentally, the vertical line test and the horizontal line test together, if both are passed, a function is called 1 to 1, which means it is a function that has an inverse. And that's a pretty important, it's a function whose inverse is also a function. Here's a function where the inverse is not a function because it's technically 2 parts. So, just something to work on. Now, when we talk about inverses, a lot of times we need to verify that 2 functions are inverses. So take this function here. F of x equals 4x plus 3, and g of x equals x minus 3 divided by 4. If you're asked to verify that f and g are inverses, you want to use this property here, that f composed of g of x equals x and g composed of f of x equals x. That's the only way to verify these are inverses of one another. So I'll do that here. First, I'll start with f composed of g of x. So remember, that's f of g of x. That means replace g of x with x minus 3 over 4, because that's what g of x is. And now in the function f, wherever you see x, plug in that function. Multiply by 4 and you get x minus 3, and then add 3 and you get x. Do the same thing in the opposite order over here. So that would be g composed of f of x. That would be g of f of x. That would be g of 4x plus 3. Wherever you see x and g of x, put in 4x plus 3. So you get 4x plus 3 minus 3 divided by 4. 4x plus 3 minus 3 is 4x. 4x divided by 4 is x. Because both f composed of g of x equals x, and because f or g composed of f of x equals x, those functions are inverses. I think that's it. It's all practice problems now. You'll do some graphing. You'll work with your calculator, working on inverse functions. Peace.